My name is Professor Ad van Wijk, and today I want to tell you something about the role of hydrogen in a future sustainable energy system. I will try to tell you what is hydrogen and what role it will play. So first of all, what is hydrogen? Hydrogen is like electricity, an energy carrier. So it's not an energy source, it's not an energy storage medium, nor is it a technology. No, it is an energy carrier. And like electricity, you can make hydrogen from every resource. From fossil fuels, biomass resources, but also from electricity and water. First of all, the fossil fuels that are hydrocarbons as molecules, you can split them into hydrogen. But in most of these cases you also produce carbon dioxide, which you can partially capture and store, as can be read in this sheet. However, there is also a technology called methane pyrolysis, where you can split the methane into hydrogen and fixed carbon or solid carbon. Then there is no release of carbon dioxide emissions to the air from this process. Another way to produce hydrogen is through the use of biomass molecules. And there you can produce it with gasification or with steam methane reforming. The important takeaway here is to see that you also produce carbon dioxide as a byproduct in most cases. But this carbon dioxide is not, of course, fossil-based, and therefore it is called green carbon dioxide, to which you can use also as a feedstock in the industry. And finally, you can produce hydrogen from water. Water itself is not an energy source, and therefore you need to put in an energy source which can be, for example, electricity. For example, you can also put the sunlight directly in the water and then split the water molecule into hydrogen and oxygen. That is called photolysis or photoelectrochemical conversion. But the most discussed and also well-known technology is water electrolysis. And that is what we see today as one of the most promising technologies to produce hydrogen without carbon dioxide emissions. There are several technologies, but the most important is called alkaline electrolysis. That is already a 100-year-old technology. In alkaline technologies, but also in electrolysis, you split the water into hydrogen and oxygen. Also other technologies exist, like membrane electrolysis or high-temperature electrolysis, where you can here you can see the chemical formulas on this sheet. If you look at the table, you see that the efficiencies of these electrolyzers are above 80% on higher heating value. You see a lot that they say it is about 60 to 65%, but then they express it on the lower heating value. The higher heating value, however, is the correct way to measure the real chemical energy content of an energy source, and therefore you have to use the efficiency on higher heating value. And when you look at the technology structure, you see all these blocks above in the sheet. These are stacks of electrolyzer cells with which you produce the hydrogen. In every of these stacks you see the cells that are the stripes you see on this sheet, and these cells are stacked to each other to make it a stack, as we call it in electrolyzer terms, a module in solar terms you would say. And if you need more output, you place more of these stacks next to each other. So the technology structure is similar to solar cells or batteries. There is not a rotating movement, there are no high temperatures, so mass productions of cells and stacks will drive down the cost considerably in the next years to come. But why do you want to produce hydrogen? That's the next question. That is because of the fact that solar and wind resources are not at all places on Earth the same. Solar irradiation is the highest in desert areas. And if you look at the yield of a solar panel over there, then that is about 2 to 3 times as much as high as, for example, in Germany. And also wind speeds are very high at several places in the deserts, but also in coastal areas and of course at sea. But normally, good solar and wind resources are far away from the demand locations. At very good resource areas, there are of course low production costs for solar and wind energy. And by converting to hydrogen at these resource locations, transport and storage costs are much lower compared to transporting and storing electricity. Because by converting to hydrogen, you can transport by pipeline, which can be also the reused natural gas pipelines. For example, here you see the pictures for Europe most left of the gas pipeline infrastructure. And in Europe we see that there is also a gas pipeline infrastructure at the North Sea, but also already from North Africa. We have a very large capacity, about 60 gigawatt, coming from North Africa with gas pipelines to Europe. And already 21 countries in Europe has now a plan to retrofit one of the large pipelines into a hydrogen pipeline backbone. If you look to the capacities of these pipelines, they are about a factor of 10 larger than the energy transport capacity of electricity cables. But also the cost to transport energy by hydrogen by pipelines is a factor of 10 lower than the same energy transport by electricity through electricity cables. So transport is cheaper with hydrogen than with electricity. And the second important aspect is that you want to deliver energy to the demand at the right time. In the graph you see the energy consumption in households in the Netherlands. The orange is the electricity consumption and the blue one is the gas consumption. Especially for heating, you see a very large seasonal pattern in the energy consumption. Also in many other countries this is the same, in Japan, Germany, but also in Russia, etc., etc. And this is already a large storage problem, because gas is pumped up from the ground at the same rate every hour in a year. So you pump up too much gas in the summer period and you store it in empty gas fields or salt caverns for use in the winter time when there is more energy demand. And if you look at the solar production pattern in the Netherlands in this case, then you see that this is exactly the opposite. It's about a factor of 8 higher in the summer months than in the winter months. So this will even increase the need for storage capacity compared to today. And you can store natural gas in the underground, in salt caverns, but you can also store in the same way hydrogen in these salt caverns. It's already in use in the UK since 1972, so it's also not a new technology. Here on the right you see the salt caverns in use for natural gas storage, with the red dots, which we can also reuse for hydrogen. Or we can create new ones in the salt formations which are also shown on this picture. To give an idea of the storage volumes, in a salt cavern you can store about 6,000 tons of hydrogen, which is about 240 gigawatt hours. And if you look at the cost to build such an installation, it's about 100 million euros. If you want to store the same amount of energy in batteries, which is of course not suitable for seasonal storage, but if you do that and you use an optimistic price of 100 euro per kilowatt hour battery storage cost, then you have to spend almost 24 billion euros. So you see at least a factor of 100 times more cost to store the electricity in batteries than to store hydrogen into salt caverns. And that's the second important reason why you want to convert solar and wind electricity into hydrogen. Because the storage costs for hydrogen are very much cheaper than for electricity. So in the end, with the conversion from cheap solar and wind electricity at these places where you have the good resources and also the space, you are able to transport and store hydrogen much cheaper than electricity, and overall cost to deliver solar and wind energy at the right time and at the right place to the demand are therefore lower than when you do this with electricity alone. So this is the first and most important role for hydrogen, to transport and to store cheap solar and wind electricity to the demand at the right time and at the right place. However, when you look at our present final energy use, currently less than 20% is electricity use. The rest is final use of fuels, or in other words, the use of molecules. Over time, we will use more electricity, of course, but you still need these molecules, especially for feedstock, but also in the industry for high temperature heating, for parts of mobility or space heating, and for storage to balance electricity supply and demand. So molecules are necessary, especially for these so-called hard-to-abate energy and feedstock use. But finally, the competition will be in price. That will be a very important role in the future. When we can import cheap hydrogen from, for example, the Sahara Desert to Germany, this will compete with local produced hydrogen and electricity from solar or wind. And then you will see that there will be much more solar and wind electricity used from the desert areas than from your local resources. But it will be in the form of imported hydrogen. And therefore hydrogen will play a very important role in a future fully sustainable energy. And let me make a final remark. Hydrogen is a circular energy carrier, because if you produce hydrogen from water by electrolysis, you use water, of course. But next to hydrogen, you produce also oxygen, which is released to the air. When you use hydrogen in a fuel cell or a combustion engine, then you use the same amount of oxygen that you get out of the air, but you produce also the same amount of water again. So really, hydrogen is a circular energy carrier. Thank you very much for your attention.